My name is Rick Astley. Although some people have been kind enough to subscribe to this channel, I only rarely post videos, and they're usually about electrical issues concerning Jaguar XKs for which I couldn't find answers on the web and had to find out for myself, and posted a video simply for the benefit of XK owners who might have also searched in vain for the same thing. This video is a little more general. I was prompted to put it together when a rare electrical issue came on my XK8, which will be the subject of another video, and at that time I was in the company of other classic British car owners, and they expressed surprise at the manner and speed with which I checked the 60 or so fuses in the car and found the culprit. In addition, from time to time I fielded electrical questions for an automotive parts supplier, and I've been often surprised by the misconceptions concerning fuses, which I thought were pretty basic and easy to understand. So I thought that having spent quite a lot of my years looking after issues concerning automotive circuit protection, I might add something to the subject, especially relating to Jaguar XKs. I'll mostly be talking about this kind of fuse. It's used in the Jaguar XK and indeed in most European cars. It's got various names. It's often simply called a Euro fuse, but it's also known as an ATO fuse by the Little Fuse brand, ATC by Bussmann, and ATS by Zeeman. In the US, the mini fuse tends to be used. It's got a similar form factor, but it's quite a lot smaller, allows higher fuse density, but actually I found it to be quite unreliable, particularly in the high current versions where the small contacts sometimes heat up too much, resulting in the spring pressure of the contacts inside the fuse box becoming rather weak. So in my experience at least, we've got much better fuses in our British Jaguars than in most American vehicles. Going back to fundamentals, what does a fuse do? Well, whether you're in your car or in your home, it protects the wiring. There may be other devices that do that too, like circuit breakers, either electromechanical or thermal, but they all protect the wiring. They're installed between the power source and the load and are basically the weakest link in the system, opening the circuit before something untoward happens to the wiring, which could include a thermal event, the term automotive companies use instead of the dreaded four-letter F word in the automotive world, spelled F-I-R-E. I don't expect you to read all this, but basically on the top right is a notice from a US company called Harbour Freight. In the UK, Machine Mart sells very similar products, but I'm not aware if or not they sell fuses similar to those at Harbour Freight. Harbour Freight were recalling fuses because they weren't doing their job of protecting, and there was the potential of firing vehicles because of it. The fuses concerned were ATC, ATO, and mini fuses, just like those we're discussing here. On the bottom left of this picture is a note from CNN about the same recall, and in it, General Motors, it's reported, put a notice out to its dealerships requiring that they not use cheap fuses. It seems GM must have found that some of its dealerships, to save money I suppose, were buying fuses from China. If GM suspected this, I'm sure that Ford, Jaguar, Land Rover, and other OEMs might have also been concerned that their dealerships are also saving money by using unbranded or unapproved fuses. Fuse selection for the OEM is not only very important, but it's very complex too. They of course have to look at the normal load current. That's a steady current that flows in the fuse after a few seconds of operation. But one very important factor is inrush current. Most loads have an inrush current which is higher than the normal running current. For an incandescent lamp, that's a bulb with a filament, it can be 15 times the normal steady current. For a motor, which is effectively stalled when first switched on, it can be 4 times the normal current. We don't want that high inrush current to blow our fuse, nor do we want it to fatigue the fuse too much. Fatigued fuses carry less current than their standard rating. That's a good reason again to choose a well-known brand of fuse, because they're designed not to fatigue very much over their lifetime. A fatigued fuse can result in nuisance blowing, which is to say that the fuse can blow perhaps when there's really no fault. The OEMs also have to consider the expected temperature of the wire. A wire that's already warm will need less overload current to heat it up past its working temperature. That working temperature could be decided because the wire above that temperature has too hot an insulation or even a melting or burning insulation. That is decided by the size and the type of wire. The size of wire obviously determines how hot it gets. If it's a thin wire, it will get hotter under the influence of a current flowing through it than a thicker wire, which will run cooler. The type of wire usually refers to the insulation. PVC wire, which is used in the cabin and most other areas of the car, will melt at a lower temperature than the crosslink wiring, which is generally used under hood or under bonnet. In some very hot areas, wires that feed components such as oxygen sensors near the exhaust are insulated with silicone rubber or woven fiberglass. Then there's the temperature of the fuse itself. A fuse that's already warm will need less energy to blow it than one at a lower temperature. This shows how the carry current of the fuse re-rates over temperature. Fuses are rated at 25 degrees C or 77 degrees Fahrenheit, that being the temperature at which they can carry 100% of their rated capacity. However, if the temperature goes down to minus 40 Celsius or Fahrenheit, then they can carry 110% of that current. On the other hand, if it should go up to 120 degrees Celsius or 248 Fahrenheit, the fuse derates to something around 86% of its normal carry current. When I refer to the size of wire, I'm actually talking about the gauge, and that gauge is normally decided by the load current. A bigger gauge wire actually has a smaller number, a 12 being bigger than a 20. Just like a water pipe, a bigger size can pass a larger current without a significant pressure or, in the electrical world, voltage drop. Sometimes the gauge size is dictated by the voltage drop that can be tolerated, particularly in the case of incandescent lamps. Incandescent lamps are very sensitive to voltage changes. A very small voltage change can cause a significant reduction in their brightness. That to some extent gets us over that inrush problem, because very often the gauge size for an incandescent lamp will be rather larger than it needs to be for its current. It maintains the brightness but can carry a higher current and be protected therefore by a larger fuse. That larger fuse is therefore able to shrug off the inrush current much more easily. Later in this video, I'm going to be testing some 5-amp fuses, so I guess it's appropriate here to mention that although I've talked of wires in the conventional sense of an electrical conductor surrounded by an insulation, the traces or tracks on a printed circuit board are also wires. You must certainly have 5 or 3-amp fuses in any modern car you own, and some of them at least are protecting a printed circuit board trace. That's because any power wire in a car, that's wire that carries measurable current as opposed to signal current, is easily capable of carrying at least 5 amps and would be protected by a higher rated fuse. In discussing fuses and circuit protection devices, we talk about a race condition. That's the race between the protecting device, whether it's an overcurrent or an overvoltage device, acting before whatever it is protecting fails. In this case, this was a trace on a printed circuit board in the instrumentation circuit board of my own XK8, and there's the reason why I had a crowd of people watching me testing all the fuses in my car to see if I could get it started. In this case, the trace obviously lost the race between it and the fuse. Vehicles and the components that go into making them are now an international business, and as you might expect, there are international standards, usually called ISO standards, that control all those components, including fuses. In this table we can see the current rating in amps for a number of fuses and the standard color code for each of those ratings. Car manufacturers, who notoriously count every cent or every tenth of a cent, pay extra for quality fuses, and in the Western world they mostly come from 2 manufacturers, Bussmann or Littelfuse. And why they cost extra is to do with traceability, the quality standards of those manufacturers, and the fact that they have these stylized numbers embossed and filled with ink on the top surface of them is a requirement of the OEMs, that's the car manufacturers, because they can robotically insert all the fuses during manufacture into the fuse boxes. And by the way, I call them fuse boxes, but they're generally not called that these days because they're much more than that. They're now generally called electrical centers or power distribution boxes because they carry other components, notably relays, and are a junction area for the vehicle's cables. But in any case, for safety reasons, it's imperative that each fuse is inserted into the correct cavity. If they're not inserted by machine, they are robotically inspected to ensure that the right fuse is where it should be, because of course otherwise there could be the possibility that a fuse may not blow when it should, or may nuisance blow when it shouldn't. The fuse on the bottom is an unbranded fuses, and these generally don't have those stylized white embossed numbers that aid fuse box manufacturing. So it's worth checking whether the fuses in your car to see if they have the embossed numbering on them and were all made by a company following the OEM's guidelines for marking. Here I show where the fuse boxes are on the XK up to model year 2005. There are two under hood. One is the engine compartment fuse box and one the passenger control module, and their locations obviously depend on whether you have a right-hand drive or a left-hand drive vehicle. One is on either side of the instrument panel fascia and one is in the trunk. The one in the trunk has a lid, as shown on the bottom left, where there are some spare fuses and a fuse extraction tool. So just run your eye over all these fuses and make sure they do indeed have that white embossed number on them showing the rating of the fuse. In case you've never seen a fuse extraction tool in use, there's one here on the left, while the most common fuse insertion tool is shown on the right. I know from experience that many people think the reason that the contacts on a fuse poke through to the top surface is for strength and stability. In fact, they're test points. You can use a circuit tester like that in the picture on the lower left to probe the fuse. One side or other should cause the circuit tester to light. If neither does, then the fuse isn't powered. If only one does, then the fuse is open. There's nothing more frustrating than an instrument that you're trying to test things with, which itself is unreliable. And so, if you don't have a circuit tester, get a good one. I would normally suffix such a comment with, and you get what you pay for, but actually I must have used dozens of these circuit testers. Some I've owned and some I've used for people I was working with, and I own a couple of these now. Is from Harbor Freight in the US. I think when I bought it, it was a little less than $4, as you can see here. It's really reliable. It's tough and it does the job very well. Some of the features are that it has strain relief for the cable at the back of the instrument in the form of a spring. It has a long rubbery cable, so it flexes very well. A strong alligator clip, itself covered mostly with heat shrink and with strain relief at the back of that too. So if you get one of these, keep one in the car. It's got a very short point, and I've tried to put a cork over that, a wine cork or something, to stop myself from being injured and to stop it from damaging stuff in the trunk. But the best thing I found was some plastic tubing with an idea, I think, of a 1/4 inch, maybe 3/16. I can't quite remember, with it cut to a bit longer than the probe itself. You can slide that over the end and it will stop it from damaging anything or you. In most cars, and in all the fuse boxes of the XK, the fuses are arranged in two rows, and up the middle of those two rows, in an area you can't see below the fuses, is a power bus. That power bus is the input power to those fuses, while the outside of the fuses to the left and to the right are the load sides. If you're probing fuses, you should find that if one is powered, there will be power on the inside test point, and if the fuse is good, there should be power on the outside as well. If not, of course, the fuse is open. When it comes to probing the fascia fuse boxes on either side of the dash, it's difficult to find a place on one of those sides to clip the alligator clip to the ground. On one side, on the left-hand side of a left-hand drive car, there is a stud that's arrowed here, and that stud is a ground point, not power. However, on the other side, it's difficult to find anywhere to get a good ground. I had to use the long lead of the circuit tester we described and clip that to the outside of the cigarette lighter outlet. Of course, we don't need to go testing fuses for every electrical problem in a vehicle. We need to go through a process of diagnosis first. I must have been asked to diagnose electrical problems on scores of British cars, and without really thinking about it, I've probably used all my senses in doing so. Sight, of course, is the most obvious one. If you see something not happening that should, a light that doesn't illuminate, for example, a motor that doesn't turn, then that's a good starting point at least. If you smell something, particularly a burning smell, then evidently that's an emergency situation. If the ignition is on, switch it off immediately. If a light is on, switch that off too. Any unusual sound that might indicate a problem is important, but more often it's the lack of sound, something that isn't happening, something the car owner is used to hearing, like a click or a clunk or a whir, that doesn't happen, and that might well indicate a problem or at least lead you toward one. Touch can also help you too. If you put your hand on the outside of a solenoid or relay and it's energized or de-energized, even though it might act quite quietly, you can usually feel whether it's working or not. If there's heat where there shouldn't be, that can also tell you where there's an issue. I must have diagnosed lots of problems with cars that crank poorly because they have bad connections to the battery. And those terminals generally get quite warm because there's a voltage drop there. There's a current flowing too, and volts times amps equals watts, and watts equals heat. Believe it or not, I have found an electrical problem using taste. By running my finger through the cocktail of fluids on a friend's garage floor and identifying battery acid led us to find that the battery was actually leaking electrolyte. Although not one of the traditional senses, the hassle factor, the need to get things done as quickly and efficiently as possible, is another thing that guides our diagnosis process. I'm going to look at some fault scenarios, some of which may result in finding a fuse that's blown, which when exchanged for a new fuse only blows again, but at least that does guide us to where the problem might lie, and it's also a good reason to have a good stock of fuses. The first scenario is to see if a single function is out. The example here is a single headlight, and if we consult the fuse chart in the owner's manual, we will find that each individual headlight is protected by a fuse, and then we have to make the decision. Is it easier to check the fuse first, or is it easier to check the headlight? In this case, it's probably the fuse. The second case here is if multiple functions are out together. The example here is the backup or reversing lamps. If both of those are out, then it would be pretty coincidental if both are out together. But of course, that's a function where you could have had a backup light out for quite a long time, and then the second one goes and you wouldn't know about it. So it might be the case that both bulbs were gone, but in all likelihood, whatever protects both reversing lights, and that's a fuse, is probably the cause of the problem. The same fuse in this particular instance also protects the rear quarter light window relay on the convertible XK, and if those windows weren't working, probably the easiest course would then be to check the backup lights, because if they're inoperative, then the common fuse that protects both them and that relay for the quarter light windows is probably the cause of the problem. Then there's a malfunction that may have a lot of different causes. The example here is a car that will crank but won't start. That could be any number of things that may have gone wrong, and it might then be worth just having a quick check over the fuses to see if one of them has blown. Again, a fuse may have blown, and when you replace it, it may blow again, but at least it could point you towards a component that has failed. If everything seems dead in the vehicle, the first thing I would suspect is the battery. To get to it, you may have to use the mechanical key, and once that battery is checked, and it could, by the way, be good one day and bad the next, if that proves to be okay, then again, this may be a situation where it's necessary to go probing around all the fuses to try and narrow down where the problem might be. Although they were designed in the early 90s, the Jaguar XKs are very sophisticated cars with a lot of computerization. In earlier cars, you could expect, for example, that the light switch would be connected directly to the lights, and the brake on-off switch or BOO would be connected directly to the brake lights. That's not the case in computerized cars. What happens there is that the brake switch, for example, connects directly to the ECM, the engine control module, and that tells the rest of the vehicle a lot of things it needs to know. Once the brake switch is pressed, it sets a flag in the computer which other functions read. In the case of the brake pedal switch, it tells the cruise control to switch off, it tells the transmission to do some things in there, and it tells the gear shift interlock solenoid to operate. You've probably noticed that every time you press the brake pedal, you hear a click in the center console around the J gate. That's a solenoid that needs to know that the brake has been pressed before it allows you to shift out of park. I'm using this as an example to show that although you may know that that solenoid is not working, testing the fuse for that solenoid would result in you finding it was good, and you may suspect the solenoid. But if you did, and that's a lot of work, you would find that was good too in all probability. If you weren't able to figure out what had happened, you might choose then to test all the fuses and then find that one for the brake pedal operation was open. This happened to me once. I'd driven forward into a parking space at a restaurant, and when I went to back out, I couldn't move the shifter. Fortunately, I knew there was a mechanical override for that, and by the way, so should you. It's in the owner's manual, and it's really worth learning how to do it, and maybe even trying it out yourself. When I got home, I started to try and figure what was wrong, and actually did think of the brake very early on. And I asked my wife to check whether the brake lights came on when I pressed the pedal, and they did, which meant the fuse for the brake lights was good too. I then went hunting around with a probe to find if a fuse had gone, and it did find one that was gone. What I hadn't realized that the Chimsel fuse, the Chimsel is the center high mount stop lamp, the fuse for that had blown, and I didn't really know prior to that it had a separate fuse from the other stop lamps. I didn't know why the fuse had gone. I changed it, and a little while later the whole thing happened again, and I found the fuse blown once again. What turned out to be the problem was that flexible cable that goes from the body to the trunk on the convertible, where the Chimsel is mounted on the lid of the boot. That wire had broken and was occasionally scraping against some metal, I'm guessing in the chassis somewhere there, or scraping against another wire that had broken in the same bundle. I had to change the wires in that bundle, and also found the one for the button for the trunk lid was also broken. And I'd often wondered why that didn't work and hadn't bothered to find out, because I could also open the boot with the remote key fob or with the button on the dash. All this is to indicate that it may sometimes be necessary to probe around all the fuses in the vehicle to find the real cause of a fault, because what seems apparent at first may not in fact be the true root cause. I mentioned earlier how important it was to have quality fuses in your vehicle, and I wondered whether it's still possible to buy fuses that are really poor, and so I went to Amazon and bought the cheapest fuses I could, and here they are. I actually bought 5 amp just because it's easier for me to test that value than it would be a much higher value, just because of the amount of current I would have to drive through them. I tested 5 of each of these fuses. I just wanted to make sure that none of the tests I performed produced an outlier that performed differently from all the rest. The one on the left is the generic fuse I bought from Amazon. I had another generic fuse, a 5 amp again, which actually came free with some inline fuse holders I bought. And I had a fuse from Little Fuse and a fuse from Bussmann, and I tested again 5 of each of those. Incidentally, we talked about the fact that all fuses are supposed to be color coded, and all these are 5 amps and all these are therefore tan, but you can see that the interpretation of tan varies greatly from manufacturer to manufacturer. This is the circuit setup I'm using to test the fuses. What I've done is I've used a variable voltage power supply to drive 10 amps through a 0.2 ohm resistor and a fuse. I've used initially a 30 amp fuse because I don't want it to blow during this setup, so 10 amps can obviously be carried indefinitely through a 30 amp fuse. I've also made sure the voltage is capped off at 14 volts. This type of fuse is actually rated to 32 volts, but when it blows I wanted to make sure I didn't have too much voltage across the fuse, because all the voltage would be across the fuse as soon as it blows, and for any arcing to occur that would not occur in a normal vehicle setup where the maximum voltage you see is around 14 volts with an alternator charging a battery. This is the same setup that I then maintained when I substituted the 30 amp fuse for the 5 amp fuses that I test. I've added a timer too, which electronically starts when the power is applied and which stops as soon as the fuse blows and the current ceases. I've now substituted that 30 amp fuse I used during setup for the first generic fuse. This is the one I bought in bulk from Amazon. The specification requires that at 10 amps the fuse should blow in a time between 0.15 and 5 seconds. That's pretty wide. The difference there, 33 times as much, the minimum, up to the maximum. So a pretty wide target for the manufacturers of these fuses to hit. That time, by the way, of 0.15 to 5 seconds applies to all fuses of this type when subjected to 200% of their rating. I've closed the switch and the current is running. Not quite 10 amps because things are getting hot, and when conductors get hot they generally get higher in resistance and restrict the current a little, so I'm continually having to adjust the voltage supply very slightly to keep it as close to 10 amps as I can. We're already way past the 5-second maximum, so let's let it run and see where we end up. The clock and the video have stopped just around 50 seconds, which is 10 times the maximum amount of time this fuse should have blown in. You can actually see it glowing if you look very carefully. In my opinion, this is an unsafe fuse and I would not want it in any vehicle of mine. The reason being that the wiring of the vehicle may well have overheated by this point and be beyond repair. We're about to test generic fuse number 2, and it actually came with the fuse holder you can see here. I bought some and never used them. When I wanted to set up this test, I looked for a fuse holder, found these, and found that they came with free 5 amp fuses. I think I bought 5, and so I had 5 fuses, all of which I used because I tested 5 of each of the fuses. Otherwise everything is the same as for generic fuse number 1. And the specification is of course the same too. If you blinked, you missed that. So it's a good fuse, and for most purposes I think it would be okay. Although it looks similar to generic fuse number 1, close inspection shows it to be quite different inside. I wouldn't be very happy using this fuse, however, just because it blew so close to the minimum value allowed, and I would be afraid that such a cheap fuse might fatigue over time and actually nuisance blow after seeing several inrush currents. Now we come to the first of the branded fuses. This is the little fuse. Other than swapping the previous fuse out for this one, everything is the same as before. This is another fast acting fuse, so I'll run the test and I think I'll run it 2 or 3 times afterwards just so you can see it a bit more clearly. I expected this fuse to perform well and it didn't disappoint. At 8 times the minimum time allowed, you could trust this fuse and you can trust this brand. You may have noticed that the meter is almost useless in this situation. The circuit is set up so that 10 amps flows through the resistor and through a fuse which is at a very low resistance indeed, but the meter samples very few times a second, and actually the display refreshes maybe only 4 times a second, so it just can't catch up with the current as it flows through the fuse. The last fuses I tested are from Bussmann, and this one here is typical of the performance of all of them. Again, I'll run the video 3 times over. So this Bussmann fuse, which like the little fuse is a trusted brand by the OEMs, performed within specification and with good margin. This picture shows the fuses after testing, and that generic one that took so long to blow actually breached its case to some extent, and I wouldn't want that to be in close juxtaposition with other fuses in any of my fuse boxes. Even the generic fuse number 2, which blew rather quickly and within specification, also burned the casing slightly. Both the little fuse and the Bussmann that performed well on time failed absolutely benignly. So that's pretty much it for fuses. I'll leave you with a picture of some fuses. The ones on the left are the ATO fuses we've been talking about, but everything I've said really applies also to mini fuses, which you can see on the right, which are mostly used in US vehicles, and also to glass fuses, which are not used very much anymore, but which have very obvious test points. And so again, you don't have to remove fuses to test them with some sort of continuity tester. Do them in situ and you'll find it quicker and easier.